Last time we started section 12.4, looking at similar figures, mostly similar triangles, and we are going to move right on into our second page of notes, where we're talking about properties of proportions. So the reason proportions comes into play here is, of course, because the side lengths in similar figures are proportional. So if a line parallel to one side of a triangle intersects the other sides, I think that should say side. That's funny. Then it divides, okay, maybe it's the two other sides, that's what it's talking about. Then it divides those sides into proportional segments. Okay? So it doesn't have to be equal segments, but they're proportional. So in other words, if you took the x value that's marked on the top left and wrote it as a fraction over the z value on the top, I said top right, like, well, we're just going to do this. If you take this one and divide it by this one, x divided by z, it will equal y divided by w. That's what it means to be in proportion. You can set them up as fractional ratios. You could also say, okay, well, I could just do x divided by y, and that equals z divided by w. Same thing. It's a similar, it's an equal or equivalent proportion to the first one. And all that takes in order for that to be true is what? What is the condition here? Parallel lines. That blue line is parallel to the side DE. Okay? Got to be parallel. But as long as you're parallel, we're good to go. Now, in particular, we could actually flip the argument around. So, if a line divides two sides of a triangle into proportional segments, that is, we know the segments are proportional first, then we know that the lines are parallel. And we saw that happen back in chapter 11 with the alternate interior angles and alternate exterior angles and corresponding angles. If we knew that those things were congruent, then we knew that the sides were parallel. If we knew that the sides were parallel, then we knew that those different pairs of angles were congruent. So the same thing's going on here with sides of the triangle, pieces of the sides of the triangle, and the lines being parallel. And what's true even more so, oh look, there's extra lines in here, let me cut this out, is that it works no matter how many parallel lines you draw through there. So you see a whole bunch of blue parallel lines drawn in here. So if parallel lines cut off congruent segments, and this one actually says congruent, on one transversal, then they cut off congruent segments on any transversal. So no matter where I draw a transversal, that's what those lines were that just erased, through here, because it's cutting off congruent segments on the left-hand side of the triangle, it will cut off congruent segments on the peach line that's cutting through as well, peach transversal. Okay? So all of those will work. And that's our final construction. We're going to divide a given segment into congruent parts. Y'all ready to do the last construction? Yeah. All right, so let me say this right now before I forget. On Monday, you need to have figured out which construction you want to kick to the curb. Because in class on Monday when we do our review, that's the deal. We will pick one construction from you guys, and I will give you one construction from me that will not be on the exam. Okay? So I'm going to show you our last construction. Maybe it'll be this one, maybe it won't, but we'll show you our last one. All right, so we've taken a look at video 13. Video 13 allowed us to use triangles and parallel lines to create segments that are congruent along a segment of arbitrary length. Mid-segment. A mid-segment is a segment of a triangle that connects the midpoints of two sides of the triangle. Okay, so as you see on AB over there, it's divided into halves by point M, right? And it's divided in half on segment AB by N, congruent segments. And there is a segment that connects M and N, and that's called the mid-segment. And there are two facts about the mid-segment. I bet you know one of them. Can you guess what one of them is? Parallel. It's parallel. So the first fact is that it's parallel to the third side. So in this diagram, what that created was that this line and this line, or there's line segments of them, but that they're parallel. Second fact. Any thoughts about what the second fact might be?
Does it make, when you draw the midpoint, it makes the sides congruent?
They were already congruent, actually. Yes, the sides were already congruent, and that's what created the ability for it to be parallel, actually.
Does it create similar triangles between the small one and the big one?
It will create similar triangles. So thinking about it from that perspective, Abby, so let's go with that. We've got similar triangles now. What do you think the length of MN will be?
Similar to AC.
Proportional because they're similar triangles. Proportional to side AC, but what will the proportion be? Half. You're right, Lacey, it's half. Okay, so now you've got the answer. Why? Why is it half of AC? But why is it half?
And A are congruent, and it has to be in the middle.
You're on the right track.
M and the bisector of BC and AB.
You're almost there.
Since they're similar, NB would be like if NB was 1, AB would be 2, so the ratio from the big one to the small one is 2, 1.
So whatever this ratio is, if this is length 1, then this is length 2. Abby's right. So the little triangle on top is half the lengths on all the sides as the larger triangle around it, right? And that's exactly what's going on. It's all related back to this idea of similar triangles. So the second fact is that it's half the length of the third side. Parallel to it in half the length. If a line bisects one side of a triangle and it's parallel to the second side, then the triangles are similar. So this second statement is almost like the reverse of the above, right? We created something that bisected, we created parallel lines. If we had the parallel lines, we created something that bisected. All right, last piece of vocab for the day, median. Last two pieces, I guess, on the same slide. A median is a segment of a triangle connecting the vertex to the midpoint of the opposite side. A triangle will have three medians. The three medians intersect at one point called the centroid, or center of gravity, of the triangle. This is a balance point. If you had a triangle of uniform density, so it wasn't like thinner on one side than the other, but you actually do, like a tile. Imagine you had a tile that was triangular shaped like this. This point is the place where you could put it on your fingertip and it would balance. Think basketball when they spin the stuff, right? It would balance right there without spinning. No spinning involved, but it would balance there, okay? You've probably seen different game shows and movies that use this idea in them, or experiments potentially at like a science museum or children's museum. This kind of a balancing point is a popular idea. The centroid will divide each median into a ratio of 1 to 2. So let's take the median, just CD, that's through the middle from the bottom left to the top right. What that's saying is that the ratio here is this is 1, then this length is 2. Here you could say it cuts it into 1/3, 2/3 segments, something like that.
So if our homework asked us to find medians,
Mm-hmm.
we just find the midpoint using like a construction and then draw the lines. Can they?
If you were asked to find a median, yes, you would find the midpoint using a construction like a perpendicular bisector, but you don't really care about the line, you just care about the point, right? And you would connect that point, say point D, to this point C on the opposite side, and you would do it for a secondary side of the triangle. That's exactly right. All right, last question then for the day. We have a lovely diagram. Did anybody still writing? I'm sorry. Are we good?
I have one more question about that.
Okay.
So is there more than those medians that it's showing? Are there more than those?
No, because a median will only connect a vertice to the opposite side's midpoint. There's only 3 vertices. C, A, and B are the vertices of this triangle. So you can only have one line through each of them to the opposite side.
That makes sense.
Yeah. Okay. We have a picture of a tree. And you might have thought at some point, sometimes you'll see pictures with flagpoles and things like that. How do you find the height of something that's really like you're not going to really measure it, right? Similar triangles is a really nice way of doing that, and you do it with shadows. Okay? So it says find the height of the tree. There's not a lot of language going on here, but you can see visually what's going on. The sun is hitting, we don't have it drawn in here, but I promise you the sun's up here. Okay? And it's hitting this tree and it's creating this shadow. And the young lady is standing over there. I say it's a lady because I'm pretty sure she's wearing a skirt. And she also has a shadow that happens to extend to the very end of the tree height. And you could certainly do that. You just have to keep walking in front of that tree until you don't see, until your shadow doesn't extend beyond it. Okay, so this is something you could physically go outside and do. If we had time, we could do it, but we don't have time. So such is life. When this happens, though, we create parallel, or not parallel, we create similar triangles because there are parallel lines here. So somebody tell me, where are my parallel lines here? The tree and the girl, right? And since those are parallel, then we're going to have proportions that are going to match here. They've got the same right angle here, yeah? And a right angle here. They've got the same angle at the top because the sun is hitting them at the same angle here and here. They actually have the same angle here at the bottom. 2 angles is enough, right? I've got all 3 angles. All the angles are matching up, so I've got angle similarity. I'm pretty sure we've got some side similarities we could probably argue through, but the angle is sufficient. So we're going to set up a proportion. So what is the height of the tree? X, or whatever letter you like. We'll let that be our height of our tree. So X is the height of our tree. What is the length of the shadow of the tree? 18. Lacey, where'd you get 18? I don't see an 18 on my diagram. Right. The way that they've marked it, the 15 only extends from the tree to the girl, and then there's 3 more beyond that. That's the extension of the shadow of the triangle. How about the girl? How tall is the girl? Ooh, 150 centimeters. What was the 18 in? We're going to have to fix that here in a minute, aren't we? Denominator, we need to know what is the length of the girl's shadow. 3 meters. We're going to have a whole bunch that we're going to do later with metric system conversions, but let me just tell you right now that 1 meter is equal to 100 centimeters. Okay? So let's change our dimensions here to all be in centimeters. So if I have 18 meters, I have 1,800 centimeters. And if I have 3 meters, I have 300 centimeters. Okay, the units do need to match. How will we solve this? Cross multiply. So on one side I have 300x. On the other I'm going to have 1,800 times 150. What's that going to give me?
270,000.
How much?
I got 270,000.
Like this? I did mine differently on my paper, so I'm following you.
Yeah.
Look good? Okay. What would I do last? Divide it by 300. So what is 270,000 divided by 300?
900.
How much?
900.
900? What would my units be? Centimeters. It's okay to leave it like that. If you were checking the back of the book, they might write it in meters. What would that be in meters, just for this argument's sake? That would be 9 meters. So either of those would be the height of our tree.